Have you ever pondered what happens to a curve as it stretches towards infinity, or how it behaves when it seems to edge closer to a particular line but never quite touches it? Well, the answer lies in the concept of asymptotes. Asymptotes are fascinating mathematical entities that provide insight into the behavior of curves. They are essentially lines that a curve approaches as it extends towards infinity. There are three principal types of asymptotes: horizontal, vertical, and oblique. Each kind has its unique characteristics and ways of calculation. Starting with horizontal asymptotes, these occur when a curve approaches a line parallel to the x-axis. To find a horizontal asymptote, analyze the degree of the numerator and denominator of the function defining the curve. If the degree of the numerator is less than the denominator, a horizontal asymptote will exist at y equals 0. However, if the degree of the numerator equals the denominator, the curve will have a horizontal asymptote at the ratio of the leading coefficients. And if the degree of the numerator is greater than the denominator, the curve will not have a horizontal asymptote. Moving on to vertical asymptotes. These occur when the curve edges towards a line perpendicular to the x-axis. To identify vertical asymptotes, look for the x values that render the denominator of the function 0. At these x values, the function becomes undefined and the curve approaches the vertical asymptote. Lastly, we have oblique asymptotes, which are neither horizontal nor vertical. They appear when the degree of the numerator and denominator of the function are equal. The formula to find an oblique asymptote is y equals mx plus b, where m is the slope of the oblique asymptote and b is the y-intercept. The slope m is the ratio of the leading coefficient of the numerator to the denominator. As for the y-intercept b, it can be found using this formula. B equals the limit as x approaches infinity of y minus mx. Asymptotes serve a critical role in understanding the behavior of curves as they extend to infinity. For instance, if a curve has a horizontal asymptote at y equals 1, it's understood that the curve will edge towards the value 1 as it extends to infinity. Similarly, if a curve has a vertical asymptote at x equals 2, the curve will approach the x-axis at the point x equals 2. Oblique asymptotes, on the other hand, can model more complex behavior, such as population growth or fluid flow. In essence, asymptotes are a window into infinity, providing us with a glimpse of the behavior of curves in the vast expanse of the mathematical universe.